But speed in the practice you need to solve 1 hour at least 20 to 25 problems faster. Need 180 questions. 3 hours. Per hour 60 problems. But biology okay. You need to concentrate more on biology and chemistry. Physics challenging. So target that to be the end. Okay. Far enough. But the assignment mode. Okay. Yeah. Okay. Mod of any number is possible. Help the iPad wire mod of mod of any number is positive. Square root of x square is mod x term. So x secant y is equal to x square is equal to 4 in what is the value of x?
Plus or minus 2.
And the plus or minus 2.
No mod.
Plus 2 the square of 4 da minus 2 the square of 4. That is another mod secant theta is this. Shall we get started? Those are online. Sorry guys, I had some doubts here. Shall we get started with the next chapter? Right. The very small chapter. Okay. Hopefully by this week itself we can complete. If not, maximum by next Monday. Okay. Those who are online, can I have some response from you? Am I audible?
Yes, sir.
Yes, sir.
Yeah, perfect. Okay, we'll get started. Right. So listen to this. Coming from the beginning. Okay, we'll come from the beginning. The first chapter is electric charges and fields. Second is electrostatic potential and capacitance. Third chapter is current electricity. Fourth is moving charges and magnetism. And if you proceed, the fifth chapter is magnetism and its matter actually. Okay. So if you come from the beginning, the reason why I'm starting from the beginning is the first topic I'm going to discuss is something about charges only. So listen to this carefully. Okay. So when we started from the beginning, the first chapter we dealt with charges which are at rest. Whenever you talk about charges at rest, what field comes to your mind? It is electric field. Okay. Similarly, we saw what will happen to the charges or dipoles placed in external electric field. We learned about the concept of potential energy. We learned about the concept of amount of torque experienced. Right. Sorry. The torque experienced by a dipole placed in external magnetic field. We have seen these kind of things, right? Torque experienced by an electric dipole placed in external electric field. You remember? Torque is equal to P vector cross E vector. Right? We saw all those concepts there. The same got extended in the previous chapter also. What was it? In the case of moving charges and magnetism. In moving charges and magnetism also, we saw what happens when you take a current carrying loop and place it in external magnetic field. What will happen to it? It will experience torque, right? But the most important concept that we need to understand here is, even before we get started, the previous chapter says it is moving charges and, what is the word there? Moving charges and magnetism. Here also we are using the word magnetism and its matter, right? Now the question is, why two separate chapters? First question is, why do we need two separate chapters for the same concept? right? So if you see, the answer to that lies in the prefix of the previous chapter. What is the prefix of the previous chapter? Moving charges and magnetism. So the first two chapters were speaking about the charges at rest which generated electric field, and the previous chapter was the one which told us if the charges are put into motion, you will be able to generate magnetic field, right? But the question is, if you need magnetism to get generated on a temporary basis, what do I mean by temporary basis? As long as the charges are in motion, then we deal with the concept of current generating magnetism. But if you see in nature, what happens is magnetism is not generated only when there is a current carrying conductor. The simplest part is we also know about materials which have permanent magnetism. Are you able to understand? So to put it simple, when you look at chapter 4, right? When you look at chapter 4, what does it speak about? Moving charges generate magnetism or exhibit the property of magnetism, right? If these charges are brought to rest, what will happen? Will magnetism still be exhibited? It will not be, right? Means these kind of magnets are going to be temporary magnets. Why? Because they exhibit magnetism only till the time you're going to pass current within it. Else, it is not going to. That is why we also call them as electromagnets. Basically, electromagnets are temporary magnets. Why? Electro refers to charges, magnet refers to magnetism. So if the charges are generated using electricity, we call those kind of magnets as electromagnets. But what did I say? In nature, apart from temporary magnets, we do have permanent magnets that are existing. So when I talk about permanent magnets, there are again two categories that can come into picture, which is going to be natural and artificial. Meaning, for these kind of permanent magnets, what is not needed? Electric current is not needed. Even without the presence of electric current, these materials will be able to exhibit magnetism. That is why the name of the chapter is Magnetism and its Matter. Meaning, we will try to understand some chemical properties of that substance. Chemical in the sense, don't worry, I'm not going to get into the molecular formula or anything. I'm just going to talk about the nature of that substance using some basics that is derived from a concept called as solid state. That is, we'll be discussing about these kind of magnets like paramagnets, diamagnets, and ferromagnets. So these are all actually these are all understood with the help of little bit of chemistry. It comes from the basics of solid state. But again, to repeat it, I'm not going to go deep into the solid state physics also. I will only discuss about the first part, that is magnetism, and certain materials. The second part deals with certain materials which can exhibit magnetism differently. That is why if you see those magnets are classified into three main categories like para, dia, and ferromagnetic. Okay, that is what the objective of this chapter. I hope you could understand what is the difference between the fourth and the fifth. So just to summarize, what does the fourth chapter deal with? Temporary magnets means you need electricity to generate magnetism, whereas in this chapter we are going to deal with permanent magnets where you don't need any electricity. That material by default will have magnetism existing. So when I talk about permanent magnets, again there are two types. One is natural and the second is artificial. Our concentration will be on artificial, because when you talk about natural magnets, they are not that strong. Though they exhibit the property of magnetism, they are not going to be that strong that they can be used for real-time scenarios. So you need to do some modifications to it and create a permanent magnet artificially. Is that point clear? So this is the introduction of what we are going to do in this chapter. But before I proceed to what is the first topic that we are going to deal, right? Question is, irrespective of whether you are going to talk about an electromagnet or a permanent magnet. I repeat, irrespective of whether you're going to talk about an electromagnet or a permanent magnet, the important thing that needs to be in our mind is, for magnetism, you need to put the charges in motion. What is it? For magnetism, you need to have the charges in motion. That is the thumb rule, no doubt in that. Right. Having said that, we told that permanent magnets do not need any electricity to exhibit magnetism. But the question is, where do they acquire magnetism if the charges are supposed to be in motion? See, there is a twist, no? We are only contradicting ourselves. We are saying that the charges need to be in motion for magnetism to get generated. So with that logic, what did we do in the previous chapter? We made those charges move artificially by connecting a potential source. So as long as the potential source is connected, as long as the current is passing, like as long as the switch is on here, this fan is going to revolve and there is going to be magnetism generated around the wires that is there. As soon as I switch it off, what will happen? Magnetism is dead. Okay. But when I talk about a permanent magnet, see, for example, I talk about a permanent magnet. You know what is the name of this? It's a bar magnet because it's in the shape of a, a 5-star bar, a chocolate, right? Right. It's in the shape of a bar. So we call it as a bar magnet, right? So this is a permanent magnet, but this is an artificial one. The natural magnets cannot be generated like this. Okay, it is made by us. Okay. Question is, I take it close to other magnets. See, you're able to see. I'm doing a thing. I'm just okay. It is automatic. It is experiencing some force. Whereas in the other direction, maybe I take it here, it will be in a different, it will behave in a different way. So it is repelling. Okay, I'm able to sense it actually. Question is, where is this getting its magnetic property from? Who are those charges which are already moving within this for that magnetism to be exhibited? Did you understand my question? It makes sense. Well, that's what you told, no? Moving charges will generate magnetism. Who is moving inside this to generate magnetism? The answer to that is given by the atomic structure. So when you talk about any material, for that matter, you and me, right? Anything in this world is made up of atoms. And what does atom consist of? It has subatomic particles like protons, neutrons, and the electrons. And electrons, what are they going to do? They are going to revolve in a orbit, right? They're going to revolve in an orbit. So for them to revolve, there is something called a centripetal force that needs to be maintained for it to be in that circular path. I'm not getting into those details, but the important question is, they are in motion. Since those electrons are going to be in motion, what will they start generating around them? They are going to generate magnetic field. That is why if you see, the very first topic that we need to answer before getting into any other topic is the magnetic dipole moment of a revolving electron. Okay, if you observe in your textbook, right, in your NCERT, this is given in the previous chapter. But I consider this as the building block for this chapter. That is why I'm teaching this as the first concept. Am I clear with this? Right? Did you understand why we are studying this and what we are going to study about? Right? You can just make a quick note of whatever story I told you from this page. How many of you sitting in this room want to do business? Have interest in business? Want to do? What do you want to do? You have not thought of it, but you want to do a business. Is there any field that you like? Fashion design. Good. You want to be a designer or you want to be a part of that industry? You want to be a part of that industry. Designer. You know how to design. Huh? Oh, she designs. Oh, you have a boutique. Where? Wait. What is it? Oh, it's yours only. Okay. That's good. But you want to take it to a bigger scale. Anyone else? All want to go for a job? Day, Britos, yeah, Sogama irka. எதுவுமே வேணாமா? உனக்கு என்ன பண்ணும்? இவ்வளவு பெருசுல இன்ஜினியர் அதுல என்ன பண்ணும்? தெரியும், அது தெரியும். That's it. So அது வந்து you want to upscale it. Need a? What do you want to do? You want to aeronautical. Good. Need a? MBBS. ரெடியா இருக்கியா? உனக்கு பண்ணணுமா இல்ல வந்து பண்ண சொல்றாங்களா? உனக்கு பிடிக்குமா? ஷூரா? What about you? Good. After that, what do you want to do? No idea. But you're sure that you want to do BARC. Good. Neema? Me MBBS. Sure are here? Same. You want to do or no choice, sir, Andrea? Okay. Shall we get started? So the first topic of this chapter is magnetic dipole moment of a revolving electron. Obviously, where is an electron going to revolve? In its orbit, right? So we are going to talk about how many ever valence electrons are there. We are only going to take one valence electron and understand what is the behavior of it. Okay. So if I take an electron that is revolving in an orbit, and let me say its velocity is like this. Okay. Now, the central part is called as the nucleus. It consists of protons and neutrons. And let's say this distance is Rn. Okay. Now tell me one thing. If this electron completes one revolution, see, all I need to answer is I'm sticking to the same basic again. When I take this material, inside this material, what do I have? I have atoms, and I have taken one such atom and trying to understand how this electron is behaving or how much magnetism this electron is able to generate when it is revolving in a particular orbit. Is that right? So it is going to be Rn. Now, the question is, I first need to understand how much current is able to get generated by this electron in one revolution. Right? I'm interested to find out what is the value of the current generated by this electron when it is revolving in, when it is completing one such revolution. So what is the formula for current? It is basically the amount of charge flowing per unit time. So what is the charge here? It is E divided by how much time does it take to complete one revolution? It is going to take time of 2 pi Rn. Oh, sorry, 2 pi Rn divided by B. Distance by speed. Right? So this will be E into V divided by 2 pi into Rn. N is a subscript. Okay, don't write it beside. It will become the orbit number. So R, below that you should write the 10. Okay. So I hope I'm clear till this step. Now the next question that I need to answer is, how can I write this current in terms of a concept called dipole moment? Because what is the heading? I am trying to understand the magnetic dipole moment that is generated by this electron. If I go back to the basic definition of magnetic dipole moment, small m says it is equal to the amount of current that is generated multiplied with the area of that coil. Am I right? So we have learned this in the previous chapter, NIA. Right? Instead of N, I'm writing it as 1 because I'm taking only one orbit. Okay. So what is I? E into V divided by 2 pi Rn into what is going to be the area? Pi Rn square. Pi R square. Rn will cancel this Rn square once. So what is that you have? Pi and pi will get cancelled. you have E into V into Rn, the whole divided by 2. So what is this? This is the magnetic dipole moment. So let me call this as 1. Let me call this as 2. So I'm still sticking to whatever they have asked us to do. They're asking me to find what is the magnetic dipole moment of a revolving electron. Now, the question is, I can say that this is the value. What is it? M is equal to E into V into Rn, the whole divided by 2. Okay. Now I want to stress on one more point. Listen to this carefully. We could have left the answer like this. I could have told that this is the value of magnetic dipole moment that is generated by this electron. But when it comes to practical purpose, if I ask you to calculate the value of this magnetic dipole moment inside the atom and tell me, you can never do that. Reason being, you know what is the charge of the electron? V stands for the speed with which it is revolving, and Rn stands for the radius of the nth orbit. So it is practically not possible for us to calculate this V and Rn. So you need high-end equipments to find all those things. So what we will do is, in general, whenever you write a mathematical equation, you should always be able to write that formula, so-called formula, in terms of parameters that are easier to be calculated, right? So for that, what I'm going to do is, okay, just a small change in the symbol alone, just to not confuse you, okay? I'll use capital M here. So here also I'll use capital M, where capital M stands for magnetic dipole moment. This is capital M. Now what I'm going to do to this expression is, I will multiply and divide it with small m, that is the mass of that electron. I'll tell you why I'm doing that. So when I multiply and divide it with mass, so what will I get? E into mv Rn, the whole divided by 2m. Makes sense? What is this value actually? This is what the magnetic dipole moment is. But still, this is also not possible for us to calculate practically. That is why what we will do is, we will try to understand what this mv into Rn is. It's called as angular momentum. M into V is called as linear momentum, whereas M into V into perpendicular distance is called as angular momentum. Let me explain what that angular momentum is, because it is a vector quantity and you need to understand how the directions work. When I talk about linear momentum, right, linear momentum is mass into velocity. So for linear momentum, whatever is the direction of velocity will be the direction of linear momentum. So it is easy to say the direction, whereas angular momentum makes use of the concept of cross product of vectors. So actually, if you see, angular momentum is represented by the symbol L. L vector is equal to R vector cross P vector. So basically what you need to do is, you need to curl the fingers of your right hand from first vector towards second vector in the shortest direction possible. Okay, what are you supposed to do? You need to rotate the fingers of your right hand in which direction? In the shortest direction possible. Having said that, R vector cross M vector, if I curl the fingers, the angular momentum is going to be in this outward. Am I clear? Right. So how did I get that MVRN to be angular momentum? Is because, observe, L vector, what did I say? It is R vector cross P vector, or you can write it as R into P into sine theta times n cap. If I take only the magnitude, L will be equal to RP sine theta. So here R stands for, so you're able to observe this electron is revolving about this axis, right? So R is Rn, P is M into V, sine of how much is the angle between both? 90. So sine 90 is 1. So MV into Rn should be replaced with angular momentum. Make sense? Right? So this will be equal to E into L the whole divided by 2m. So I'm dealing everything in scalar quantities. Observe. Magnetic dipole moment is a vector quantity. Angular momentum is also vector quantity. I told you how the angular momentum direction is. In this case, how is it? R vector cross P vector. It is towards us. It's towards us, right? So we need to take that into consideration. Finally, I will write how the directions of magnetic dipole moment and angular momentum are related. Is it clear till this? Okay. So let this be the third step. So let's come from the beginning for this page alone. It's very simple actually, okay? Just because there are some concepts which are derived from your 11th standard, I'm trying to go slightly in depth. So if you actually look at the derivation, it's very simple. First thing, what did we do? We understood how much is the value of the current that is generated by electron in one complete revolution. So I is equal to charge by time. So for charge, you directly wrote the value of E, and for time, you wrote it as 2 pi Rn divided by Vn. Okay, V. So 2 pi Rn is basically the circumference distance by speed. When you write it, you rearrange it as EV divided by 2 pi Rn, which is equation number 1. Second step, what did we do? We wrote the mathematical formula for magnetic dipole moment, which is current multiplied with area. So current, I took it from the first equation, substituted here. Area is pi r square. I wrote the same thing. R will get cancelled, pi will get cancelled. So you will be left out with E into V into Rn, the whole divided by 2. So from this, it is not possible for us to calculate the speed. That is the reason why we are trying to write it in terms of known quantities. For that, what is the manipulation we did? We multiplied and divided with mass of the electron. When you multiplied and divided, what is it you got? E into mvrn divided by 2m. mvrn is what is called as angular momentum, right? So I wrote it as L divided by 2m, and I'm calling this as the third expression. But this is also not the final answer, because angular momentum is also not possible for us to find. So what we need to do is, we go with a very important condition that is stated by Bohr. You have learned about the Bohr's orbit and everything, right? Bohr's structure of an atom, Niels Bohr, right? So there is something called as Bohr's quantization condition. So the Bohr's quantization condition says, when an electron is revolving in an nth orbit, the angular momentum is always quantized, and the angular momentum is given by the formula nh divided by 2 pi. Okay, this is derived from your chemistry. We'll be learning about this in atomic physics also. It will be in 12th chapter. Atoms. So L is equal to nh divided by 2 pi, which is 4. Now what I will do is, I'll use the fourth expression in third. When I do that, observe what I'm going to get. So I'll get capital M is equal to E divided by 2m multiplied with, in the place of L, I can write it as nh divided by 2 pi. Now observe this expression. It is easy for us to calculate all the values. So this is going to be n into EH divided by 2 pi into m. Make sense? Yeah, 4 pi, I'm sorry. So correction here. It will be n into EH divided by 4 pi m. So I can say that this can be used as a formula because the orbit number, it is easy for you to find. Right? Charge of the electron is known. H is Planck's constant. It is a constant. 4 pi is a constant. Mass of the electron is known. So this magnetic dipole moment is written in terms of all the quantities that are known to us. Am I clear? Right? So this will be the value. And if I put n is equal to 1, if I put n is equal to 1, what will the value of capital M come out as? E is how much? It will be 1.6 into 10 power minus 19. H is 6.626 into 10 power minus 34 joules second. Okay. The whole divided by 4 into 3.14 into 9.1 into 10 power minus 10 power minus 31 kilogram. So everything is in terms of SI unit. When you substitute all these values, you will get a constant value. Okay, it will be 9.24 into 10 power minus 24 ampere meter square. Okay, which is called as Bohr's magneton. Okay, so first copy it till this step. Directly or indirectly? கொடுக்கணும் கொடுக்கணும். Anyone having NCERT, no? You're done with this page? Done? Okay. So when you calculate this value, it will come out as 9.27 into 10 power minus 24 ampere meter square. And what is this called as? This is called as Bohr's magneton. It's called Bohr's magneton. I hope it is clear. Is it clear? Right. Shall I proceed? Okay. So this is about the first part, that is understanding how the atoms are actually able to generate magnetism. So having said this, right, since everything in this world is made up of atoms, right, including you and me, what will happen is every material will possess magnetism. But we are not able to execute it or exhibit it because of the extent to which that value is getting generated within us. So within certain materials, this value will be more, within certain materials, it will be less. Is the point clear? Having said that, we'll move on to the next topic, that is the concept of artificial magnets. So when you talk about a natural magnet, it looks something like this, which is called as magnetite. Okay. Now, this is a natural magnet. But what happens with a natural magnet is, it will not have enough strength to magnetize other materials. Let me explain what I meant by that. Okay. Let me show you a small sample. So I've taken this you would have already played. See, I've taken 3 bell pins, right? I've taken 3 bell pins. I've just kept it randomly like this. I hope those who are online are also able to see. Now, what I'll do is I'll take this and attract it. But what I'm going to do is the other bell pin, I'm not going to attract it directly with the help of magnet. Rather, I'll use this end magnet, take it. And third one, I'm trying to, but not working much because, see, the first one has contact. The second one is taken with the help of the direct bell pin, right? And third one, if you see, it has no contact with the magnet itself. How is this able to happen? So what is actually happening with this? So let's visualize it, okay? This magnet has what present around it? It's a region, right? It's magnetic field that is present. Due to the magnetic field, what will happen is, first of all, this first bell pin that got attracted, right? It will get magnetized. In the sense, here what I've done is I've taken the south pole closer to this first bell pin. First, in the sense, I'm talking about this one. So this one. So when I took the south pole closer to it, there will be a magnetic field induced in it in such a way that this will become north pole. And the other end will become south pole. So there will be a small structural rearrangement that will take place so that there is a magnetic field existing within this also. Are you able to understand what I'm trying to say? Right? Because if I reverse and put it, it's still going to work. So what has happened this time? Things have changed. Right? So when I take it, so by default, this pin does not have anything like north pole and south pole. So what is happening? Because of this magnet, it is able to create a magnetic field within this, and this magnetic field is strong enough to attract other magnetic substances also. Meaning, if I remove this also, what you are able to see, it is still able to hold it. But do you think it will happen for a longer duration? I'm expecting it to fall sooner. But I kept it in contact for some duration, it is still there. So this property that is attained by this pin is what is called as retention, or you call it as retentivity. Are you able to understand? So this is not a natural magnet, but it is a magnetic substance. There is a difference. What is a magnet? Magnet is something which can exhibit magnetism, but magnetic substances are the ones which can have magnetism induced within them. Okay. So what is this? Magnet. This is a magnetic substance. A magnetic substance, and this is what is an example of ferromagnetic substance. Why it is ferromagnetic? Because it has a lot of retention. See, still it is able to hold. There is no magnet in my hand. Because this has attained magnetism, due to which it is able to produce or share it with the other material. Okay. So why I'm telling this is, when you talk about a natural magnet, the ones which are naturally occurring, right? will not be able to create this level of impact, due to which there is no practical applications based on it. Ultimately, when you discover something, that's what science says, you discover something for some purpose, or else you don't need it, right? So this one does not exhibit that level of magnetism, so though they are naturally going to occur. That is why what we need is, we need artificial magnets. So when you talk about artificial magnets, there are different kinds of magnets that can be generated by us. Depending on the shape that you give to that magnet, they are classified into different categories, out of which the first one, you can call it as a bar magnet, which you're able to see it here. Just the difference of red and blue is given for you to identify. See, for example, I was holding it this far. So north is written here, south is written here. Suppose I hold it like this, first thing you will not be able to understand which is north and south. So there needs to be some differentiation. If suppose I give a color, this is red and this is blue. From there also you'll be able to tell that this is North Pole, this is South Pole. That is the reason why it is given like this. Okay, only for you to find out something, right? That is a bar magnet, right? It is a bar of circular or rectangular cross section. Mostly it will be in the rectangular cross section. Okay. Second is, you can think of a magnetic needle. So what is the magnet? Where do we use the magnetic needle? We use it in a compass. So how do those magnetic needles respond? If you observe, you have seen compass, right? So when you take that compass and place it like this, you can see that the magnetic needle will move like this. It will move down like this and it will keep rotating also. It will oscillate and rotate. Why is that happening? So what is first, let's understand what a magnetic needle is. Magnetic needle, it is a thin magnetized steel. You can think of this bell pin. This bell pin was holding the other bell pin. No, the first bell pin, which was holding the other one, is what is called as the magnetized steel, because it got magnetized. It attained magnetism. So these are all the terms you need to be careful, okay? Because in the next part of this chapter, there are many terms that will come which will confuse. Magnetization, magnetic induction, magnetized, magnetizing. These terms will be used. So it is basic English only. So concentrate on what I'm saying, okay? So what is the meaning of a magnetized steel? The one which has attained magnetism, right? So magnetic needle is something, it is a thin magnetized steel needle having pointed ends and is pivoted at its center. Pivoted in the sense it is, there is a small screw that is put and it is hinged, right? At its center, so that it is free to rotate in a horizontal plane. So you'll not hold a compass like this and see. Have you ever seen anyone? They'll not hold it like this. You'll hold it in this way because we need to navigate in this direction. With respect to us, we are going to navigate on a horizontal system. This is north, this is south, this is east, and this is going to be west. Are you able to understand? That is why it needs to rotate only in the horizontal plane. Now, for this also, if you see, there is a small color differentiation that is given. What is it? Red for north and just left as silver for S, south. Third is a horseshoe magnet. You have seen this, right? So what is this horseshoe magnet? It has the shape of a horseshoe and that's why the name. And lastly, the other type of magnet we can think of is a ball-ended magnet. So at the ends, you will have two magnets in the shape of two balls. So again, red and blue. So mostly red is used for north and blue is used for south. Okay. So I hope this part is clear, right? There's something which is a basic from your lower grade only. Just a recollection. Right? Do you want to copy this or shall I proceed? You have it in your mind? Okay. Now, the next important part that we need to understand is what are the basic properties these magnets can exhibit. Right. So when it comes to the conceptual understanding, we need to know the basic properties. And when it comes to the exam perspective, these concepts can be used to frame assertion and reason based questions. Because assertion reason questions are framed only to confuse you. So you need to be strong with your basics. Okay, there are few points which speak about the basic properties. The first property is called as attractive property. So what is the first property of a magnet? It is the attractive property. Question is, okay, it is attractive, fine. Is it not going to repel? It will repel, but the most important property is only attractive property. Whom are they going to attract is what the question is. So when you talk about a magnet, it attracts small pieces of iron, cobalt, nickel, etc. Okay. So when a magnet is brought near a heap of iron filings or iron fillings, whatever you call it, basically it is the powdered piece of irons. Have you ever seen it? Actually, I was supposed to have, but it's missing. It'll be in brown color shape, right? It'll be fine particles. Okay. When you bring those iron filings, what will happen is the ends of the magnet will show greater attraction. Why? Why are the ends of this magnet showing greater attraction? Because ends have the poles. So where is the magnetic strength the maximum? Near the poles. So North Pole and South Pole, when you observe how the iron filings are going to get attracted, they will take this kind of a shape. You see, the density of filings are going to be more near the poles because it has greater strength compared to the length. Am I right? So that's what they're saying. Near the ends of the magnet show the greatest attraction. These ends where the attraction is maximum are called as the poles of the magnet. And the most important point to be noted here is magnets obviously have two poles, right? Magnets always have two poles. That is why this every is very important. Why I'm telling this is very hard. Okay. Suppose I give you this magnet. Let's say you're breaking it into two parts. You have the North Pole here, South Pole here. If I break it into two parts, can I say that my left hand has North Pole and right hand has South Pole? Can I say that? You should not say. Even the smaller pieces. So if I break it into two parts, imagine there is a chocolate. Okay, you break it into two parts. Left hand, you're going to have a piece. Right hand, you're going to have a piece. Left side has North Pole. Right side has South Pole. So when you break it, what will be our assumption? Left hand holds North Pole. Right hand holds South Pole. No, but that's not true. When you break it into how many other pieces, you're actually breaking into small such dipoles. Means the very important point to be noted here is, unlike electric charges, magnets cannot have monopoles. When you talk about electric charge, you can talk about an isolated positive and isolated negative, but you can never talk about an isolated North Pole or isolated South Pole. North and South Pole always exist as a pair. So when you break it into small piece, that small piece is going to be there, no? That will still have North Pole and South Pole. If you break it even more smaller, that will also have North Pole and South Pole. But what will change is the strength of it. This will definitely have a greater strength compared to half of this. So this will have a lesser strength compared to double of this. So what is the important parameter that is important here for this? Its length. You're able to understand? But that's what they're trying to tell here. Every magnet has two poles. Okay, what are they? Obviously, north and the south pole. So we'll try to define what that north and south pole is also. Okay. First, I'll explain, then you can copy it. Second, there is something called as directive property. What was the first one? Attractive property. Here we are talking about directive property. What is it? When a magnet is suspended or pivoted freely, it aligns itself in the geographical north-south direction. Okay. So maybe just give me a second. Okay, we'll try that and see how it is rotated.
So we are not able to hear you. Sir,
Am I audible to people who are online?
Yes, sir.
Is it audible? Okay, sorry guys, I have to repeat this. They didn't hear. See, what I'm saying is I have the North Pole and the South Pole. Now I'm going to suspend it freely to understand what the directive property is. Okay, but I need to do a validation also. Who's going to tell me whether it is right or wrong? I'll use a compass to check whether it is right or wrong. Okay, so listen to this carefully. When a magnet is suspended or pivoted freely, it aligns itself in the geographic north-south direction. As I told you, right? Whenever you talk about the north and south, there are two types of north and south. What are they? Geographic north and magnetic north. Similarly, geographic south and magnetic south. So here they are stressing on this important point, that is the geographical north and the south. Okay. So remember, this is north, this is south. I'm going to suspend it. Okay, let it come to some. It is actually experiencing torque. So I'm expecting it to rest. So what is happening here is I am able to see that this direction, this is what, this is south actually. Let me check. Yeah. So if I hold it like this, whether I'm going to hold it in this way, anyway I'm going to hold it, you're able to see it is aligning itself. I'm trying to twist it in whatever direction I want. It is still trying to align itself only in this direction. So it is aligning itself in the direction of geographic north to geographic south. So I know that this is south. Okay, but let's validate it. So I'm going to show you here. You're able to see? It's working? Right. So it will work in this direction in such a way. See, for people who want to see it, right? I'm just bending. Are you able to see?
Yes, sir.
Yes. So that's how it works. This is the meaning of directive property. And this is the idea that is borrowed to design magnetic compasses. So because how does it know that this is the south direction? Somebody has to tell you. It is because of this property, we have that device which is important for directions. For you, it is very important. Right? I hope you understood why it was. Navigation, right? Yes. So you need to understand that. So the pole of the magnet which points towards the geographical north is called as the north-seeking pole, or it is also called as north pole. If you try to understand, here this magnet, they have given me the specification already. So I know there's north and south, but what will happen is if I take this needle, for instance, I want to design my own compass. What do I need to do? I need to first magnetize this. If I magnetize this and tie a thread here and hold it, it will start facing in this direction. When it faces in this direction, by default, what can you say on the activity that we did? This is south and this is north. Though this needle does not have any specification on it. But how did you confirm it? Because of the directive property. Make sense? Now you are able to sense what actually north and south pole means. Here the north and south pole actually means the geographic north and the geographic south. Clear? Right? So the other pole which is pointing towards the geographical south is called as the south-seeking pole, or you simply call it as south pole itself. Okay. So why is this property important? If this was not there, your Google Maps will not exist today. Our life would have been horrible. They made so easy, no? Uber integration with Google Maps. Simple technique, but look at the scale at which they are operating. Right? Next. See, this one is known to you. Like poles repel and unlike poles attract. This I've already shown. There is nothing much to show. See, let me take, I don't know which is north, which is south. It's not given here. But one thing I can test is this south pole. It's getting attracted. This is getting repelled. So this is south pole. This is going to be south. If I bring the north here, it is attracting. So like poles are going to attract and like poles are going to repel and unlike poles are going to attract. This is a known property, right? So that's what they're asking us to do with the help of this activity. I take 2-bar magnet, suspend it, you can still experience it, right? Not a big deal. This is another important point. Magnetic poles always exist in pairs. Magnetic poles always exist in pairs. If we try to isolate the 2 poles of a magnet from each other by breaking the magnet in the middle, then each broken part is found to be a magnet with a north and a south pole at its end. If we break these parts further, each part again is found to be a magnet. So what will happen is, unlike the electric charges, there is no concept of magnetic monopole. Magnets always exist in the form of a dipole. Di is 2, pole is polarity. Make sense? So this is also a simple property. And the last important property, this is also I've shown it to you. Magnetic induction. A magnet induces magnetism in a magnetic substance. Magnet induces magnetism in a magnetic substance, right? Magnet induces magnetism in a magnetic substance placed near it. This phenomenon is called as magnetic induction. See, why we call it as induction is, you need to understand 2 things, okay? So induction is a word that is used when you create a field inside a material without a physical contact. If you read the statement carefully, they are not saying that you bring them in contact. What is happening? Magnet induces magnetism in a magnetic substance placed close to it. In the sense, if I take this and place it close to this, you're able to see it. You see it is rotating. I'm not twisting, okay? It is rotating. So how is it happening? This is south pole. So what is happening inside this? Magnetism is induced, due to which what pole is getting generated here? It will be north pole. So it is turning, getting attracted. Now this is getting attracted. Now what you can do is, to make the changes, you can keep in contact with this for, let's say, 5 minutes. Then you try to bring the other end should repel. You're able to understand? So that should work actually, right? So when a north pole of a powerful magnet is placed close to a soft iron bar, the closer end of the bar becomes south pole. That is what I told you. North pole is placed near a soft iron bar. Instead of soft iron bar, we use a bell pin, right? The closer end of the bar becomes the south pole and the farther end should become the north pole. As a result, the magnet attracts the iron bar, and this induction precedes to attractive property. So that is why we never speak, whenever we speak about magnetism, right? We never speak about repulsion. Magnetism, we always speak only about attraction. That's why the properties are important. Are you able to understand this point? Right? So what are the 5 properties? Can we come from the beginning? Just to summarize it, make it quick. First is attractive property. Second is the directive property. Third is like poles repel and the unlike poles attract. Fourth is magnetic dipoles. When you break them into smaller pieces, yes, it always exists only as a dipole, no monopole. And the 5th property is magnetic induction. That's it. That's simple, right? So these are the 5 properties. If at all they want to frame any assertion reason based question, they cannot frame anything outside this. Is it clear? Since you have visualized, I'm assuming that you can answer any type of question that comes, right? So just make a quick note of it. I'm assuming that you already know the points. Do I need to show this or you remember? Okay. So if at all anybody wants to copy this, make it fast. So you can just take down the keywords from it, right? Take down the keywords. Okay. Next card. Last point, right? Magnetic induction. Okay. So what is the time? Okay, we'll stop with this. Next class, there are a few more derivations that I'll start with. Okay. Those are online. Any questions? All clear?
Yes, sir.
Okay, then we'll wind up.
Yes, sir.
See you guys.
Thank you, sir.
Yeah.